Do you feel good? Yeah, a little bit. Okay, so we will have some more interesting keynotes here in the afternoon, and so far, thank you so much for your cooperation and great ideas, so please continue with that. I know that a lot of the things we hear here are complicated stuff, and in order to do that, you need a really sharp brain. So what I do very often after lunch, when your brain is getting a little dizzy, I do a little brain break. So I want to just do that with you, just to wake up your brain. So could you, with your right hand, do like this? Or left hand, sorry. Yeah. Okay, that's easy. You're doing pretty good. And the other hand, you take the little finger like this. Oh, that's easy. You're doing really good. And now the brain training part, because now you have to shift really fast. If you're good at it, you can do it many times. Yeah. Okay, I can see the DTU people are better at that than in Siemens. So, anyway, when I was working at the Danish Institute of Technology, which I did for many years, working with innovation, one of my colleagues, he always told me, he said, if you want to travel fast, then do it alone. If you want to travel far, then do it together. And to me, that's also when we saw the future maybe coming to us in 2030. If we travel together, we can go really far. But now it's time for the next speaker, Jan Madsen. And Jan Madsen, he's head of section at DTU Compute. And really look forward to hear what you have to say.
So, now it's on. Okay. So I'm going to talk about healthcare, and I'm going to talk about a specific part of healthcare, which is point-of-care devices, under the title Nanoscale Guardian Angels, and I'll come back to the meaning of that. So if we think about healthcare, a lot of us are thinking about lifestyle, using gadgets and things like this to help us monitoring our performance in daily life. And there is this movement of quantified self, which is the idea that you can measure things about yourself, and then you can, you can get this onto your mobile phone. Maybe it's the mobile phone itself that are doing it, and you can list all sorts of things that you can monitor. This, of course, you can have more things you are monitoring, and then you get a better understanding on your health and performance. And the idea of the quantified self is also that you can share that with others. So you can put it into the cloud, and then you can share and you can compete. And it's nice. The challenge here is that this is what I would call nice to have. If you talk to doctors, they don't like it that much. Because if you are watching over tracking your daily health, you're getting a lot of curves, and it's nice when it's going up, and certainly it goes down, and then you think you're ill, and then you get to go to your doctor and so on. So that it's, from the doctor's perspective, you're just getting more sick people. I mean, that's that you have to address. So I'm not going to talk about quantified self for these. I want to go back into the doctor's place and looking for how we can use technologies to help patients. And one of the things that we're interested in is that if you have a disease, maybe you have problems with your heart, you go to your doctor, he may get you to the hospital, you stay there in a period, and they monitor you while you're there. And they're looking at the rhythm and all of this, and then they send you home and say, come again next month or in 3 months, and we can measure you again. The thing is that in this period in between, we don't know what happens. And this may be repeated, but we still, I mean, everything works fine when we're in the hospital, but then the problem comes when we are not in the hospital anymore. So we can do things, we can start monitoring continuously. So the idea is that you may go to the hospital, you may get the first diagnosis, and then you can have a device you carry that will continuously monitoring you, and maybe also be connected with the doctor so that he or she can follow you. So even when you are in your private sphere, you can sort of look at things. This can also allow you to add more modalities to it, so you can get a better picture of the thing, so you can measure different things. And by correlating this, you may be able to get a much better understanding on your health situation, and maybe also being able to detect some very early warnings of changes in your condition. And this is what I would call need to have. So, where does the guardian angel comes into place? Now the thing is that if you think about it, at least that's my view on this, I don't want to be having to be confronted with these data every day. I would like to live my life without thinking about it, and just being warned when there is a need to be warned. And this is exactly what the guardian angel is. And the idea is, can we turn technology in to help us in doing this? So I know that I'm being watched, and somebody in this case is the technology, takes care of watching over me, and I don't have to worry. Only when I really have to worry, and then that's a different thing. Now, of course, this requires a lot of computing power and things, and you have that from the whole dimension, from the cloud, where you can do massive computation, into the mobiles, where you can track things and you can interact as a user, into what I call the sensor swarm. So that's a lot of small computing devices distributed, maybe on us, maybe in us, maybe in the environment around us, that helps in capturing all this data. Now, there are some trends that I will talk about and show how this can be used. So one thing is that these technology development comes in waves, and we of course know that we have gone from the Industrial Revolution into the Information Revolution, and we have had the computer going up dramatically. The next one is more in the distributed intelligence, and then there is the next one was started, that's the nanotech, that has a lot of potential. And you can look across these three fields, and then you can see you have some capabilities in nanotech, you have more in the distributed intelligence, and a lot of power in the computing, and you can bring these things together to actually get to this vision. If we look into the technology, then we know there has been some trends in here. Most of you are familiar with Moore's law, so that's the one that tells that every second year or so you can get double amount of computing power on a certain size of a chip. And this has been going down and down all the time, and a lot of focus on it. This is where we integrate computing a lot. But there's also another dimension, which is the horizontal up here, which is also called more than more. And that one is integrating different things. So not only electronics, but also going into having sensors, mechanical devices, and even into biochips, and I will come back to that. So if we look at these possibilities from the point of care device point of view, we could ask ourselves the question is, so if we talk about care, so what do we mean? What is it we want to care about? Where do we want to do it? How are we going to do it? And when are we going to do it? And there is, of course, a lot of challenges. If we look at a system like the one over here, it means what are the type of sensor technology we have, and how could we deal with this? Can we make most of these self-powered? So that's another interesting thing. So I want, even though they are electrical and they need to get power, I don't want to have batteries. I just want them to create energy out of the environment. And there's a lot of issues in security and privacy when we start capturing a lot of data that we share or actually exchange. And there's also in how do we actually go and deploy this. So if we start looking into one aspect, being able to monitor things. And I'll give you some examples. I'll also tell what we are in my group are looking at, but also some other things. And the first one here is one way of looking at putting sensors onto you. It's not something we are doing, but it's a clever idea of actually trying to turn electronics into a way that it's stretchable and bendable. And what this one is actually ECG environment where you can capture the signals, you can transmit the signals, and so on. So you have a small computing device that you can stick onto to your skin. And it's developed out of a very nice way of having bended wires in different materials that can form the different components that you need, like transistors, photodetectors, and so on, but still be in a way that you can actually move the things around. It's a very nice concept. Now, if we look at healthcare, it's fine that I can monitor things, but what happens is that when I have something, a stroke or whatever it is, what I do is I go to my doctor. The doctor may take a blood sample. This blood sample is then transmitted to a lab. The lab spends some time in analyzing this. The result come back to the doctor, and then finally I can get my result out of that. This is tedious, and you could start thinking about scaling in the terms of how we have been scaling microelectronics. If all of this is about decision making, well, maybe we can have a computer doing this. But what about the lab? Well, why not think about the lab? Try to scale that and put it into the smartphone as well. So do all the things there in a lab. This is actually possible, and this is where the technology is now evolving into. One of the projects that I'm involved in, it's together with DTU Nanotech, is a project where we're actually trying to do a lot of this. It's an EU project. And the idea is that you build a small sensor chip that you can put into your smartphone. And on this one, you have a small lab. You put in a drop of blood. It's purified through some chemical processes. And then in the end, it's passed over a sensor. This sensor is a nanowire. And on this nanowire, you have some receptors that can identify specific molecules in the blood. And in one of the cases that people in the project are looking at is early markers for cancer. And because this is a nanowire, even a few molecules you can detect by a change in the electrical field over the nanowire. And then that will be able to detect what you can do. You can think of this as a weighting device, very, very fine weighting device. And you can get these measurements. Now, this part you can build, and it needs to integrate. So you have, of course, a lot of integration with electronics. So changing signals into digital signals, managing those, and actually having an interface on the smartphone. So we are in the process of getting a prototype of all of this that actually works together. So the whole system integration is an interesting part as well. Okay, so measuring is one thing, but maybe also controlling is something that we want to do. And we know of this image of people with diabetes, where you have to measure your blood sugar level. A group of people in our department has been working on the idea of building an artificial pancreas. And so it's a device that can actually substitute the natural way of regulating your blood sugar. And in order to do this, you need to understand how the physiology works. And when understanding this, you can build a model of it. So you can actually, out of sensing the level of blood sugar, you can make decisions about what to do with the insulin. And you can actually make predictions into the near future. Now this model you can pack together and you can put into the computer that is controlling this. So you have on the body, and this is a prototype that is being tested, you have measurements directly on the blood sugar level, and you also have insulin pump that can actually put out the right amount of insulin, and then it has the model of your body or the workings of that part of it, and can predict how much you want to dispense. A little bit like the forecasting of the wind in windmills and so on. It's again one of these predictive modeling systems. But we can take this even further, because we can actually start thinking about implanting devices. And this is a device from EPFL in Switzerland, It's a small computing device that you actually implant into the body. And when you have done this, it's not so nice to put batteries in there in that sense. So their idea is that the batteries is in a plaster that you put on your skin, and it transmits wirelessly energy into the system. And inside this system, you have, of course, the electronics, the computer, the wireless transmitter, so you can get information out. But you also have small compartments where you have these small biolabs, where you can actually measure liquids in the body and making decisions based on that. So again, you get it from the person into the mobile phone, and from the mobile phone you can transmit over the internet to the doctor. Now, I've talked about this scaling down the lab and putting it into a small chip. And the last part of my talk, I will give you some examples of what this looks like and what the potentials are. So this is actually a lab on a chip, one of the more complicated ones, but I will come back to this. So basically what you can do is plumbing at the nanoscale. So it's just small channels where you can put liquid in. Here you put first the green in the bottom, and then you put some yellow in the top. And then by exercising valves fast, you can start getting the liquid to circulate, and then you can mix it. And when that is done, you can take the mixed value out and you can go somewhere else. So you can do all the basic operations of mixing, diluting. You can have small sensors that looks at it, counting things. And this you can do on a very, very small scale. This is one of the technologies that people are looking at. Another one is like this one, where you work on droplets. So from a reservoir, you can spin off small drops. You can move those around. And here is another drop coming in. When they match again, you move them around, and then you can get them to mix. But on these small scales, we're talking about droplets in the size of nanoliters. It's very, very, very small you can work on. And you can actually capture cells inside each of these, and then you can see, not by doing how cells react when you have billions of them in a small flask or something, but you can actually look at what's going on while it's going on for single cells. And that means that you have the potential to do conditional experiments in biology, which is something that have not been possible before. You set up a lot of experiments, you design the temperature and all of this, you see what happens, and then you try to change some of the parameters, you do another experiment, you look what happens. Here you can actually change things while they happen. So just like as a computer scientist, this is what we do. I couldn't think of myself writing a program where I wouldn't have any control structures. So it means writing thousands of programs to try to solve something and see which one of them actually solved my problem. That would be completely meaningless for me. But now we start having some potential tools that allows biology to work in the same manner. So what does it mean in terms of scaling? Now this one is the first computer from 1971. It's the Intel 4004. It had in the order of 2,300 transistors, the small contacts that is actually making control of how the current flows in the design. The example I showed you, this one, is from 2002, and it has 2,056 valves that you can control. So sort of same complexity, but completely different technologies. So there is like a span of 30 years, but if you start plotting this into and looking at Moore's law, you have the first, so algorithmic scale, you have the first computer, and then you have those of today, which have billions of transistors, the largest one, 20 billion transistors today. And if you look at the early stages of lab on a chip, here, the one with 2,000, some of those we see today get even higher. And it's actually been shown that you can reliably produce, on 1 square centimeter, you can produce 1 million valves. Well, then there is not space for much more, but it gives you an idea about the complexity of these chemical labs that you can actually build in very, very small place. Now still today, most lab on chips have no active components, no valves. It's just pushing liquids in and seeing what's going on in there and doing stuff. But there's a lot of things you can do. But the trend is that we are going in this direction, and there's a lot of potential in doing this. And that brings me to the final slide, which is a nice picture from Scientific America some years ago, which is a vision of where it could bring us. So this is a device to measure maybe blood pressure and things like this, and it's inside a blood vein. So what it has is that it has the computer with the transmitter and everything, and it has some storage. It's not a battery. The energy it's harvesting from the blood flow in the vein, and this is done through a huge amount, billions of nanowires. And these nanowires, whenever they bend, they change charge. And you can have them bending, and then they can hit a small device on the top, and then they give loose on this energy. And if you have enough of it, you can start sampling a lot of small energies, and then you have enough to do something, and then you can do a measurement, and then you wait for it to gain enough energy again. So I think the scene that we will see is going to change very dramatically with these technologies, which is really, really scaling so we can get them in anywhere, not just in healthcare, but also in environmental monitoring and so on. Yes, that brings me to. Thank you.
Thank you. Thank you, Jan. I really look forward to the day you can produce implantable devices with microphone inside the body, so you don't have to do all this stuff all the time.